So welcome back to another video of Robo CNC. I'm Marcel. It's been taking way too long, but this is the next video in the Plasma Build series. In a previous video you have seen me use these awesome servo motors, and you may have noticed that they spin things around. Now, spinning things around is quite cool, but what I need is a linear motion. So one of the methods to convert rotational to linear motion is to use trapezoidal or Acme threading, which is typically a square or almost square type of threading, and often seen with these brass nuts. Now, the problem with this is it has in the beginning quite a lot of friction, often these brass nuts, and after a while you get quite a lot of play. So if you change direction from left to right, there is what they call backlash. Acme threading or trapezoidal threading is often used in 3D printers. Also in cheap CNC machines, and it's often seen with conventional mills and lathes, so that are not converted to CNC. Now, if you're a normal person and you're building a plasma machine that's not as heavy as the one I'm building, a super interesting way could be using timing belts and timing pulleys. They don't have the backlash problem all that much. They're dirt cheap and super fast. And so there is a big reason why I not opt for going with the belt system, and that's because belt has a bit of movement or lack of tension in the belt, and this could create movement in a side-to-side, sideways fashion when we apply forces to the side of the z-axis. And while in plasma that's not a big problem, when I convert the machine to a CNC router, I want to withstand forces in the lateral directions. So if you're not new to this channel, you have seen me build multiple CNC machines. And if you are new to the channel, shame on you. But most of the time when I build CNC machines, I use Ballscrews. We can see it here in the z-axis, we can see it here on the Gantry, and we can see it in a lot of other videos. Why? So here we see a ball screw and a ball nut up more close. And although it looks quite similar to the trapezoidal, if we look closely to the thread, you can see that the shape of the thread is circular. And that's circular because inside this ball nut there are balls. And these balls are like ball bearings, and these balls are selected so they really are a tight fit with these grooves. And in doing so, you create that although there's not much friction when rotating, there's also no play like there was with the trapezoidal. Now the balls inside here are rotating until they come to this plastic cap. So they travel around, come to the plastic cap, and then go back to this plastic cap and travel around again. This specific ball nut has two races with balls inside there. This sounds ideal, but why am I not going to use this in the plasma build except for the z-axis? Well, the reason is this shaft or this ball screw is 12 millimeters in diameter, and if I make that really long, like more than a meter long, it will start to wobble, for the lack of finding a better English word that I know. So it starts to wobble and shake and vibrate the whole machine. Now, of course, I can get 16 millimeters or 20 like I had in the router you just saw earlier. I can also go to 25 or 30 millimeters diameter, and then probably the wobbling part will stop. But what is the disadvantage? I have a very long ball screw with a very large diameter, and that results in a lot of mass. Having a lot of mass spinning around fast means I have to accelerate that lot of mass and I have to decelerate that lot of mass, and that lot of mass has a lot of inertia. So it has a lot of inertia resisting to do the acceleration and deceleration. So we have been talking about what not to use, so let's start talking about what am I going to use to drive the linear motion on the plasma machine. That's going to be rack and pinion. So this part is the rack and it consists of teeth, and this part is the pinion, and that's going to be driven by the servo motor. But as you can imagine, this is not really a beefy one, so let me help you select the best rack and pinion that we can now find to build this machine. So we're back at the computer, Autodesk Fusion 360, where I made a rough drawing of the machine that I'm trying to build. So this is the Z-axis and that's driven by a ball screw, and we made that one in another video, so check it out. This is the gantry, right, and for my case I'm going to call it the Y-axis for now. This Y-axis is going to use the rack and pinion, and I'm going to mount it on top of this beam. I'm going to mount one rack and one pinion to drive this system, and it only has to move the Z-axis, so let's say roughly 20 kilograms of mass. Now the other thing that's going to be driven by the rack and pinion is this axis, which is called the X-axis for me, and I'm going to drive it with, on the left side, a rack and a pinion, and on the other side also a rack and a pinion. So still, this is going to be driven by two motors, but the mass is going to be much more than twice the Z-axis, because this beam is really heavy, as you've seen in the previous video. So yes, I could take a different motor for each axis. I can choose a different rack and pinion for each axis, but I'm not gonna do so. I'm lazy and I like to keep it simple. So let's do all the calculations just for this long travel here and see what the best rack and pinion system is. So what I eventually want to do is select the right servo motor, select the right rack, and select the right pinion that is then in his case driving on top of that rack. Now to do so I need to know the amount of force, the total force that is required to move this gantry over this complete table. And to calculate that I should be a mechanical engineer, which I'm not. I'm a jack of all trades and a master in none. Well, I have a bachelor in electronics, but not a mechanical engineer, and I will make mistakes and you will find them down in the comment section below, because this is YouTube. So make sure to check out the comments to find out my mistakes. Now the total force is the sum of all forces, and let's try to figure out which ones those are. Well, the first one for sure is the inertial force, or the acceleration force. I have a certain amount of mass that I want to accelerate, so get to speed in a certain amount of time, and that's going to for sure be a force. Now in a plasma machine you would maybe not expect an external force, so something that is pushing on the gantry or on the axis in the different direction. But since I'm also making a router, you can imagine that moving a big router bit through hardwood is going to imply a force on the tool bit, and so let's call this the cutting force. Well, gravity. Well, gravitational force might in some cases be something to consider. Frictional force. I mean, we're gonna use a beautiful heaving rail and that has a low friction coefficient, but even heaving rail has friction. Nothing is free in this world, and probably also the bearing has some preloading. We will grease it, maybe with thick grease that is sticky, so there will for sure be frictional force. Now, before you head over to the comment section, know that probably at the place where you live, the gravitational force is pointing downwards from the place where your machine is standing. Now, in case of the z-axis, definitely something to take into account. But in our case, for the rack and pinion selection, which is the x and the y-axis, the gravitational force does not directly impose the horizontal movement, and so it does not appear as a separate force in this calculation. So we can cancel out the gravitational force. However, the gravitational force does have an effect on the frictional force. The weight of the moving part, which is the gantry in our case, presses down on these linear bearings, and this increases the normal force. And the normal force in turn increases the frictional resistance, even though gravity itself is not acting on the direction of motion. Now, before I start calculating the best option for the rack and pinion, I want to show the easiest way, which is go to Google, type Apex Dynamics, go to the website, and on this website you find all the information you need. So go to the contact page, fill in all the details about your machine, and at Apex Dynamics there is a guy working there. He's like a superhero. He asks you a few questions and then he tells you what the best rack and pinion system is. Now, we of course not gonna use superheroes at this moment. We are going to try to understand the selection process of rack and pinion system ourselves. And to do so, let's start by getting the catalog. Menu, downloads, go to the catalogs, find the rack and pinion system, and first let's have a look at all the information that we can find in this beautiful catalog. So since we want to select the right rack and pinion system for the CNC machine without the use of a superhero, I started reading into some engineering dynamics from R.C. Hibbler to find out all the formulas needed to do these calculations. And also the Apex Dynamics selection guide shows a lot of the calculations and steps to take when selecting this product. So that's a very nice resource also. In creating this document, let's start with the legal note. I'm fully responsible for all the calculations made here, and you are fully responsible if you want to use it, because it's on your own risk. Do the selections you want, check the document, and if you have some feedback for me, note it down in the comment section. Know for sure that Apex Dynamics did not create this document, they did not check it, and they did not ask me to make this, so it's fully on me. So that's the right side of the document, the legal note. And of course, first watch this YouTube video when you use this document, because I'm gonna take you step by step through this document. The next thing is that you could be one of the contributors. I mean, I made this document, but probably I made mistakes, and probably you guys have great ideas to fill in, make this form even better and make it some sort of open source. So maybe we should convert it to Google Docs or something, and maybe you have an idea to add pages, like if you have a cool document for feeds and speeds, or if you have a document that creates the same calculations for ball nut and ball screw, For instance, we can make more pages or more sheets inside the same document, and you will become one of the contributors. Now, this document is on the right side. We see all the steps that we have to take, and they refer to the green one, the blue, and the red part. So let's start by filling in the green part of the sheet, which is the CNC application. Now, these orange-ish fields are to be filled in by you. The gray fields are calculated. So we are now doing the longest axis of the CNC application, which is a horizontal axis. So fill in horizontal. Now it should carry the full gantry up and down the motion, and I estimate it to be roughly about 115 kilograms. So let's take half of that, because 2 rack and pinion systems and 2 sets of motors are going to drive this axis. Now, cutting forces is a whole new rabbit hole. If you want, on a plasma CNC, it would be 0. There is no force that is pointing on the plasma tip, or unless you crash. But since I'm going to use a router on this machine also, I have to take into account that the router bit travels through the material. So like a big router bit going through hardwood, for instance. This sets an external force or a cutting force. Calculating this is a whole new rabbit hole, and maybe one of you guys want to make a sheet that calculates that stuff, because it's a lot of variables. I say let's call it about 300 newtons, so about a 30 kilogram pushing on the router bit as a maximum. Now, the end velocity. I want the machine to run about 25 meters per minute at its maximum velocity. It's just a number. So that's about 0.42 meters per second. Now about the acceleration, which is a big part of the force that the machine is going to be encountering. You have to think of a number. I think about 0.35 of a second to get from 0 to full speed. It sounds like a bit much, but also take into account that it's also deceleration. I mean, if the machine has to stop, you want it to stop quickly. So I say let's 0.35 seconds. Now what's the length of this axis? It's 2950 millimeters. That's the longest axis on the machine I'm building. The frictional coefficient mu, I set it to 0.1, and why do I set it to 0.1? Because of reading into the Hewin linear bearing guidelines. They say it's even less than 0.1. Reading on the internet, most of the people are using 0.1 as a rough guide to the frictional coefficient. These ball bearings have, well, they have friction, of course, although they're rolling, so it's really not much. But these bearings also have some preloading. Preloading, some thick grease inside these blocks might also increase the friction. So let's put it on 0.1. And now all these cool numbers are in there, and I even put in a safety factor of 2. I mean, if you're building bridges, you're not gonna estimate the biggest truck that's going to run on your bridge and calculate everything based on that exactly. You're gonna multiply it by some number. I'm multiplying it by 2 to give me some margin of error, because I'm gonna make mistakes. So now the gray fields are filled in, and you see the machine is going to run at a maximum speed of 25 meters per minute. It has an acceleration of 1.19 meters per second square. So that's the accelerational well, the acceleration. Accelerating the axis or the gantry from 0 to maximum speed would take about 73 millimeters, so 7.5 centimeters. That at full speed means that if you travel the full distance, you will have 6.7 seconds of full speed travel. Take also the acceleration and deceleration time into account. That means that the travel distance is the full distance from stop till stop is done in 7.5 seconds basically. Gravitational force is 9.81 meters per second squared. Probably where you're standing, it's roughly the same. And that's used for the frictional or the normal force, and therefore it's taken into account when calculating frictional force. And if you're building a vertical axis like the z-axis, it's used for the gravitational force also. Now we see we have 4 forces that are calculated. The first one is the inertial force, and the inertial force is due to the acceleration. So you have a big mass that you have to accelerate from 0 to the maximum velocity. So you see it's F is m dot A, the mass times the acceleration, and it's about 70 newtons of force. Now the external force that we put in was 300, so that's not calculated, or well, it's calculated by you or me and filled in. The gravitational force would be 560 newtons, but is not taken into account since this is on horizontal axis. The frictional force is about 60 newtons, and you see that frictional force is mu times n. N is the normal force, and the normal force consists of the mass times the gravitational or times gravity of 9.81. So it is in there. The sum of these forces is 425 newtons. That's the expected force on this axis. Now in green you see that the maximum tangential force in the second load direction is double of that. Why? Due to the safety factor. We put in a safety factor of 2, so I multiply it by 2 and come to roughly 815 newtons in the second load direction, which is the tangential. So well, you can see it here in this picture. It's in the direction that the axis is traveling, so not in the direction the motor or the pinion is feeling its force, but the second load direction, which is the linear version, not the rotational. Now finally section 2 or section blue, where we're going to select the rack and the pinion. First step, do you want a straight or a helical rack? I'm going to go for a helical rack. And let me take you to this website of Apex Dynamics. Google it. It's interesting to read the difference between a helical and a straight rack. Now, often a straight rack is a bit more, or you can find them less expensive than the helical racks. On the left you see a picture of a straight rack, and on the right you see a picture of a helical rack. So basically it has an angle. And this angle has some advantages and one disadvantage. The disadvantage is you are creating a lateral force, so a force that is directed into the gearbox and into the motor. My gearbox and my motor can easily handle that, and for the machine it has a left side and a right side, so these forces cancel each other out. Now a helical rack runs a lot smoother and a lot quieter, and it can handle more torque. And basically the reason for that is that with a straight rack you have one teeth or one tooth that is in contact with the rack and the pinion at every moment in time. With a helical you have 2.2, so there are more than one teeth connected or in contact with each other at the same time. So this is very nice. There is another interesting read, and that is this part. If you have a helical design, and if you like calculating, do this stuff or read it for yourself, you now have a normal number of the hole spacing, so an integer number for the hole spacing. If you have a rack, a straight rack, and you have multiple racks, so you buy 1 meter sections for instance, you will get a really strange hole spacing. If you have a single rack with a normal hole spacing, that's not a problem, but I'm gonna make it into multiple sections. So this makes mounting and aligning them much more easy for me. The next selection is the rack and pinion quality. Now, if I take you to the PDF document we just downloaded, you see they have quality between 4 and 10. Now, if we look at 4, it has an accuracy where you have a deviation that is less than 20 microns per meter. And this is used for measuring equipment and laboratory environments. Maybe a bit much for us. Number 10 is having like 146 micrometers per meter deviation, and that's used in like elevators and stuff like that, loading mechanisms and rough robot arms. Now, it might be a bit too rough, so let's look into the middle. Quality type 6 has 33 microns of deviation over 1 meter, so that's a pretty nice number, and it's used in water, laser, plasma machines, portals, bending machines, woodworking machines, and in combination with linear guides. Sounds like something that is appropriate for our machine, so I'm gonna go with Q6. The next thing is to select the number of pinion teeth. Now, selecting the number of pinion teeth, you hear a lot that 20 teeth is the optimal number. And Apex has a page, why does the ideal pinion have 20 teeth? So read it. It's most fabricators of rack and pinion advised against small pinions. So let's say 15 to 17 teeth is the absolute minimum. But if you go below that 20, the gear shape, the geometrical shape of creating it becomes more hard. They have to change the involute. So look at figure C. Might be a bit of exaggerated, but you see like you need this round shape in the bottom to have gear contact or engagement. When you have 20 teeth, you can leave the geometry optimal. So pros and cons with less than 20 teeth. So a disadvantage would be you have lower torque due to this geometrical shape. Faster wear, low resistance of breakage, but the advantage might be more precise due to the small diameter. If you go more than 20 teeth, this thing is of course the other way around. They are less accurate. And why? There is always a little play in the drive, and the big diameter basically magnifies that error. Now, there are some other pros and cons, but I think we can just go and check if 20 teeth is feasible for us. I mean, if you have a real big pinion, you will also travel a lot further per revolution, so probably I will have to have a gearbox with a high reduction ratio, which is also not really ideal. So I'm gonna try at least to find a 20 teeth pinion for my system. So the last step in filling in section 2 is selecting the nominal module. Now let me take you back into the Apex selection guide, and this bottom figure shows the module. It basically tells you something about the shape or the size of the teeth. Now module 12 is really big, and it will have a large load capacity, so you can do push a lot of load. Now module 1 on the other hand has a much lower load capacity but a much higher resolution. So in my case, for a CNC machine, I want the lowest module possible because of the high resolution, but it has to withstand the load capacity, of course. Let's go to page 50 and see what I come up with. I want a pinion with helical teeth and a keyway. So I come to this page and then see module 1. Module 1 does not have 20 teeth pinions. It starts with 30. So I selected 20, so let's go up one number. Module 1.5. Module 1.5 does have the 20 teeth pinion. So let's try and go with the module 1.5. Module 1.5 filled in, and now we can see that all the gray fields again are calculated. The angle of our helical gear or pinion and rack is 19 degrees, 31 minutes and 42 seconds, which is equivalent to 19.53-ish degrees. This makes that the pinion diameter is around 32 millimeters, and well, 32 millimeters feels like a normal size for this machine, so I'm totally fine with that. Now comes the beauty here. The travel distance per revolution is exactly 100 millimeters. Now, my OCD likes that a lot, so every revolution the machine travels 100 millimeters, liking that one. The F2A, which is the force, as you can see in this apex picture, is the force that points into the gearbox or the motor, is around 300 newtons. So it is something. So people that are against helical gears are right. There is really a force pointing that way. Same applies in F2P, upwards, the vertical force. But not really interested in those two. I'm interested in this green one, because T2B, which is the maximum torque that is expected, which is this arrow here, so around the shaft, so the torque that the gearbox and the motor needs to deliver, is around 13.52 Newton meters, and this is already including the safety factor. It is calculated based on this F2T, so this 13.5 is already including your safety factor. Now the last step stated here in section 2 is to check if this F2T, so the force in the linear direction, and T2B, which is the torque that has on the pinion, are to be delivered by the selected pinion and rack combination. So let's get back to the document. Again, we selected module 1.5, 20 teeth, and there are 3 of them. I selected the third one because I already know the diameter, the internal diameter of the shaft that I need. So I have this number here to order the correct pinion. Now let's scroll down until we find a bit more information about this pinion, and which is here. So the module 1.5 20 teeth has an F2T of 5027 newtons. So the force that this pinion and rack and pinion system can deliver or withstand is more than 5000 newtons. If I look back in the document, what I need is 850. So it's not gonna break any teeth, that's for sure. Going back, we see that T2B, the torque that can be delivered by the pinion, is 80 newtons. If we look back in the document, what we need is 13.5. So 13.5 is much lower than 80. So again, the torque is not a problem either. Even the module 1 would have been sufficient. Yeah, it would have been sufficient, but they did not have the 20 teeth that we wanted. So we're gonna go with 1.5. Going back up in the document to page 18 brings us to the rack itself. So checking the rack that we selected, 1.5 module with a length of 1 meter. So they have them in 500 millimeters and 1000 millimeters. Is available, and we can see the ordering code over here. Congratulations, you have now calculated the correct rack and pinion system based on actual calculations of force and torque and without the use of a superhero. So again, this is a complete system. You need a servo motor or a stepper motor, you need a gearbox probably, and you will need the rack and pinion. So do not order your rack and pinion yet, make it complete. And to do so, we're gonna go to the red section, which is the gearbox selection. Now I already know what motor I'm going to use, which is a clear pad servo, and it runs 2980 RPMs. So I fill that in. I can right off the bat see in green that the maximum gearbox ratio will be 11.92. So if I go above that 12 gearbox ratio, I cannot reach the maximum velocity or speed of the machine. So let's say we want a gearbox ratio of 10. Let's go back to the website of Apex, go to their menu, downloads, catalog, and through the magic of cooking shows, I already selected the P2R PDF or type of gearbox, and I even downloaded the manual. So let's scroll down and zoom in a bit to see the possible gearboxes that they have. Step 1, the nominal output torque, T2N of the gearbox. If you have a single stage, ratio 10, you can deliver 27 Newton meters of torque. Now if I look at the document again, I needed only 13.52. So seems that this might be already a good fit. Emergency stop torque is calculated by 3 times the T2N. So they say if you have an emergency stop, one time stopping really quick, you can do like 3 times that 27 Newton meters, which is nice. Acceleration torque, which is actually the torque, the highest torque that we calculated, is also 60% of this e-stop torque. So this 27 Newton meters was for us already including the 13 Newton meters was already including the acceleration. So we are absolutely safe. Backlash, something to take into account. This has less than 7 arc minutes of backlash. So there is always backlash in a gearbox, and that's also why we want a single stage, preferably over a 2 stage. 7 arc minutes, so that's 1 degree of a revolution divided by 60, and then 7 of them. Well, I might do the calculations up in the screen somewhere, but let's see if we are fine with that. Maximum input speed is 6000 RPMs. We are going to input less than 3000. And the maximum radial load is 1150 newtons. So load in the radial direction. Fine too. Efficiency of this gearbox is more than 97%. And that was something we needed to fill in. So let's put that here, 0.97% as a gearbox efficiency. So 3% of the energy you put in is lost due to heat, sound and other, well, not other things, I only think heat and sound. Do you want an extra safety factor on the gearbox? I do not want that, I just keep it at 1. already there is a safety factor of 2 in all the calculations, so let's leave it at this. And now you see that our gearbox maximum acceleration torque, so the maximum torque that the gearbox will encounter is 6.76 Newton meters on the input side. And that was absolutely fine. Some other fields, the total reflected inertia to the motor, which I might go into when selecting the motor. Well, at least you can find it in the ClearPath manual if this is okay for you. Vmax would be 20, almost 30 meters per minute if we use this gearbox ratio and motor. The total torque of the motor, the peak torque will be 0.7 Newton meters. The nominal torque 0.58 Newton meters. The motor RPM to reach Vmax will be 2500, which is nice, a bit lower than the 2980 and still in its high torque regio. And it will take roughly 182 watts of power to drive this. So these last fields are more in selecting the motor. I will go into a bit more detail on that when we do a next ClearPath video. I think this video is already quite long and there's a lot of calculations and not much machining and making chips and stuff like that. So I think we should cut the video right now. I hope you liked it. I hope you liked the document and the fact that I share it with you guys. Please be a contributor. Think of something to add to this Excel document and it might eventually become a real extensive document with a lot of CNC parameters in there to be calculated. Well, I think that would be cool. I hope you liked the video. Thank you for watching and hope to see you in the next one.